For the first one, we figure out r prime of t. We're looking at 6t plus 2 I plus negative 12t squared j plus 6k. So I need the magnitude of that. Now, in some cases, the magnitude could be pretty ugly. This is one of those cases. So we're looking at 6t plus 2 squared. The second component I could write out kind of neatly, 144 t to the fourth, in expanded form that is, plus 36. But in terms of going further with this, you know, there is validity to the question of what would be the benefit of going further. If we're just finding a unit tangent vector, there really isn't much benefit in going further. So what we would do is represent our answer in this current ugly form. All right, and that's perfectly fine. Now, we will at some point, a little bit later, have to figure out what the derivative is of the unit tangent vector. When that happens, then you're naturally going to be interested in simplifying this. But without any kind of context being given, there's really no point. So I say don't even bother. So I'm basically going to have to write the same thing 3 times. That's the only drawback to not simplifying, is that you don't have a simple expression to write 3 times. You got to write a lengthy expression 3 times. But the trade-off is that you didn't have to simplify it to begin with, so you're all right with that. What's that?
If you make an error, just copying the same thing over again.
Oh, like,
I'm probably just copying it in a hurry.
yeah, no, that's
Can you just say parameter key, and then copy it all over again? To me, it's copy.
You just write it out, but if you make a little mistake here or there, I'm not looking for that. Yeah. I've done that myself. And in fact, if this app let me easily copy and paste, I would have done that, and that would have just pissed everybody off. So. But yeah, when we talk about curvature, one of the things that we're going to have to do is find the derivative of the unit tangent vector. Okay, so I'm kind of limited in the types of questions I could ask you, because, you know, finding a derivative of a rational function is not difficult. The problem is you'd have to find 3 separate derivatives here involving quotient and chain rule. It's just lengthy. You know, there's only so many questions that I can ask that are going to be fairly elegant, right? So in the case of number 9, that you're going to see elegance, right? And so this is the kind of problem that you want to be on the lookout for, because r prime of t is equal to, well, I'm not there yet, negative a sine t I plus a cosine t j. Now I need the magnitude of that. Normally it would be 1, but because the coefficients here are a's,
You don't take now? Oh no. Yeah. So it's 8 plus what plus 1.
you square each part, put it under a radical, you're going to have that common a squared that you can factor out, which is just going to give you an a, because the sine squared plus cosine squared is going to go to 1. All right, so that gives me my magnitude. And so t of t is just going to be r prime of t divided by the magnitude of r prime of t. So basically just cancel out your a's. and you have negative sine t I plus cosine t j. And if I found the magnitude of that, it would be equal to 1. That's the whole point. When you're looking for unit vectors, the idea is that the vector itself would have a magnitude of 1. Now, a big question is, and it's a legitimate question, all right, cool, we found derivatives. What are these derivatives telling us? So for that, because this is the perfect example, I'll just draw a quick sketch. So you have a circle with a radius of a, all right? So you just draw any generic circle and just scale it so that its radius is equal to a, which is basically just labeling it as, there it is, a, all right? So what this is telling us is what the direction would be of the tangent line at any point along this curve, right? So for example, I'll just do a couple of popular values. Let's do t equals 0 and t equals pi over 2. All right, on the circle, 0 is going to put you at this location. Pi over 2 is going to put you at that location. But in terms of the tangent vector, t of 0 is going to give us something different. T of 0 is going to give us 0i so 0 in the I direction and 1 in the j direction, so plus 1j. All right, at pi over 2, I'm going to get a negative 1 in the I direction and a 0 in the j direction. Now, if I were to just plot these on an ordinary xy axis, zero, 1, vector 0, 1 would be right here. Here's 0, 1. And here is negative 1, 0. All right, so these are the relevant tangent vectors. Now, any kind of vector is going to be pinned at the origin, but what we're getting from this is what the direction would be of the tangent at that particular point. So when I'm looking at 0, for example, it's this location here. That corresponds with 0, 1, so my tangent vector should be going off in this direction. All right, so that's the 0, 1. At pi over 2, let me just make it purple. Pi over 2 is here. That's going to be going off in the negative 1, 0 direction, so we're looking at something like this. All right. And when we talk about curvature, we're talking about what is the change in your unit tangent vector as your arc length changes, right? So as you work your way around the circle, how fast is your tangent, your unit tangent vector changing, right? Because somehow it goes from pointing straight up to pointing straight to the left. What is the transition numerically, right? So if we're looking at a large value, that means that it's a very fast rate of change, so that would indicate something that's curvier. Right? If it's a small value, that means that it would be a small rate of change, and that would be a less curvy type of function. All right? But this is kind of what we're leading into. So I could find this for infinitely many points around the curve. So I mean, the rest we could just kind of eyeball. But you know, I could choose a point, for example, like right here. So I'd be looking at something, poor quality, something like this. I can grab one over here. It looks something like that. This one's, I think, is obvious, but we could work our way around the circle in that counterclockwise fashion and come up with what we think are reasonable estimates, and then you could see what the transition would be over evenly spaced increments. Right? But there is a numerical approach that we can use so that we don't actually have to draw out diagrams every single time. Right? So number 10 is just kind of a repeat of number 8. So I think we can just kind of bag that one. You're welcome to do it if you want, but I don't think it's really necessary. It's a little overkill. All right, so the concept of curvature is we're talking about the curviness of a graph. Right? So a line has no curviness, so a line would have a curvature value of 0. A circle is the definition of curviness, I suppose, and so that would have a value that's not equal to 0, but not all circles have the same amount of curviness. So if you have a small circle, there's more change, there's a more rapid change in those tangent vectors as you work your way around, right? Because really, if you just think of it as like turning radius in a car, you know, like if I have to make a sharp turn as opposed to a nice wide turn, the wide turn would be consistent with a large circle. The narrow turn or the U-turn, it would be a small circle, right? Like when you're driving at speed and you have to make a nice wide turn versus a really sharp turn, you feel it. You feel the difference. One of them is gonna, like that old TV show, I forget what show it was, but the kid was taking his road test, to try to get his driver's license, and the road test was very simple. Guy got in the car, I think it was a movie.
Spill my coffee.
Yeah, spill my coffee and he failed. Right? And so, I mean, if you take a sharp turn really fast, you're gonna spill the coffee. If you take it nice and slow and gentle, then you're not. So basically, it's really curvy if you're gonna spill that coffee. All right. So this is the idea that we're getting at. Curvature, kappa, it's just, I mean, K is fine. Right? I just draw the K like super funky. I don't do it the way that they do it, or like they as in like the creators of the Greek alphabet, I guess. I use parabolas to create it, so I make my kappa look like super curvy. So I just put a sideways parabola, upward and downward facing parabola. So that's how I mean, because really it doesn't matter what it looks like as long as it doesn't look like an ordinary K. So just make a funky K and you're good. All right, that's my funky K. All right, so what we're looking for is the rate of change of the tangent per unit of change in the arc length. Right? So there's a couple of ways to handle this. One way would actually be determining, and so this is the part that gets kind of funky. We could use the technique for putting our vector value function in a parameterized form in terms of the arc length, so get that relationship and then work it out that way. But if you follow this derivation, and you're not going to be responsible for this one because it's too much of a pain, the derivation ends up giving us the derivative of the unit tangent vector over the derivative of the arc length. But using the fundamental theorem, we develop equivalence between the derivative of the vector valued function itself, so the magnitude of that derivative, and the derivative of the arc length. They end up being the same thing. All right? And that's because we know that this is true because we've been working with this. If I were to take the derivative of this, the s prime of t, that would just become, the st would become s prime of t. But when I take the derivative of this integral, it's just going to cancel out with the integral, and you'll be left with just the magnitude, right? So that allows us to streamline the process significantly and just say, I'm going to take my unit tangent vector, take its derivative, find that magnitude, and then take the magnitude of the vector value function's derivative itself, and then what you'll have is the the value for curvature. All right, it's easier if you do it at a point. So we'll start off with a case involving that, and then I'll show you some general cases. All right, so if I'm looking for the curvature at t equals 0, I can look at the graph and get a sense of what's going on, but I could also just dive right in. All right, so what I need is basically everything at a point. So my curvature value is dependent on r prime of t, so I'll get that first. All right, so just take the derivative. I'm going to want that at 0. So r prime of 0. So I know the magnitude at, I'm sorry, not the magnitude, the derivative at 0. Now I want the magnitude of that. And that's just going to be a 1. Now you can plug that into a formula if you want, but it's just going to be equal to 1. Now I also want t of t, all right? So for that, what I'm going to do is take, because t of t I can figure out, but again, I want to do it numerically. So instead of t of t, since it's at t equals 0, I'll find t of 0, all right? So t of 0 is going to be equal to I just lost my place there for a second. R prime of 0 over the magnitude of r prime of 0. Oh, scratch that, sorry. We do need to find the t of t because it's the derivative. Sorry. So r prime of t over the magnitude of r prime of t. So 2t, 1, and we're dividing that by the magnitude of r prime. So I will have to figure that out. But that's easy enough. 4t squared plus 1 under the radical. So it's a little beefier looking, but this is what our unit tangent vector would be. Now we need to take the derivative of this, and that's what I was getting at before, but I almost skipped the crucial step that makes the whole thing work. Right, so that would have been an issue. So what I want is t prime of 0. Okay. Now notice how I'm not saying I want t prime of t, I want t prime of 0. It's very important you understand the difference between a case that's numerical and a case that's completely algebraic. Right? Because I'm asked for the value at 0, that gives me license to chuck this in my calculator and come up with the values. Because otherwise you have to use chain rule a couple of times, which, you know, if you like chain rule, it might be okay. Did. Because when I wrote t of 0, that was basically the same as replacing, you know, doing all this work and then replacing the t's with zeros, right? But it would have zeroed out and that would have been a problem, right? So,
Sorry, I'm sorry.
oh, sorry.
If that's only derivative, and you're now plugging in values at the derivative itself at different points, if it's a 0, it should be a 0, right? What can come up, what else can you have a derivative of 0? I mean, if they plug in...
If you plug in the 0 here, you make both of these constant.
Okay.
And since the curve itself is not going to be constant, you would be basically creating a situation where the unit tangent vector is always going to be 0, and that would be a problem.
It's t of t, that's not the derivative of t.
Right? Yeah, we're doing a derivative in the calculator. Right. Alright, so what I'll do is I'll just pop in both pieces to my calculator. Alpha y equals, put it in as a fraction, so 2x over the square root of 4x squared plus 1. And then same deal, just with a 1 on top. Alright, so then once I have those in, and you don't actually have to do it that way, but that's the way I like to do it, because most of the time, so math 8, most of the time, it's not just one thing that you're doing with a function in your calculator, it's usually a bunch of things, so I like to put it in as y1, right? So when you select math 8, we're finding the derivative of y1 for when x is equal to 0. So it's trying to tell us 2. It just doesn't quite have the vocabulary. And then same deal, except now we're changing it so that it's y2. All right, that's my
You just type in y2 or?
alpha trace.
Oh, alpha trace.
Alpha trace brings up all your y's. All right, so we get 2, 0 as my unit tangent vector's derivative at t equals 0. And so if I want the magnitude of that, I can plug it into the formula, but since it's only along the x-axis, it's just going to be equal to 2. All right? So to get my kappa value, what I'm looking for is the quotient of the magnitude of t prime of 0 and r prime of 0. So we get 2 over 1 and that's going to be equal to 2. All right. So curvature, the values of curvature generally are loosely defined as 1 over the radius. It's just the thing is radii are variable for certain functions. For a circle it's easy because the radius is constant, it doesn't change. But the unit tangent vector has a magnitude of 1, so if I'm looking for the rate of change of that unit tangent vector's baseline is that the vectors themselves are equal to 1, so that's the 1 component. And then this is the rate of change of the length of the vector itself. I didn't close parens there, so let me fix that. All right, so for circles it's easy, but for other types of functions it's a little bit more involved. Now, if I had to do this out by hand, or if I had to do it for a general t, not t equals 0, not a particular value, but at any time t, then I would have had to differentiate each piece of this and then put that into the magnitude formula, simplify it, before putting it into my fraction and hope it cleans up somewhat, right? So the numerical cases are a lot nicer because you can use the calculator to support your work, but that doesn't mean it's, 2 steps and you're done. Like there's still a little bit of work that comes into play, but it's not as crazy as it could be. Now there are situations where you can do it out by hand. So let's take a look at number 12, the curvature of a circle of radius a in R2. All right, so I don't need this because it's general terms. We're looking at R of t is equal to a cosine t, a sine t. All right, with these are all based off our knowledge of polar equations. And so what we learned way back when was that for circles, it's in the form of cosine sine, where a represents the radius. All right, so that's our standard model. It's just a question of, okay, what do we do from here? Well, the short answer is the same stuff we did for the other problem, except now we're gonna have to do it algebraically. So r prime of t. Now there is an element of familiarity here because this, I think, will be the third time we're working with these same values today. So negative a sine t, a cosine t, the magnitude of r prime of t, a squared sine squared of t, plus a squared cosine squared t, kind of start streamlining the approach because, you know, like I said, we've done this a few times. If I factor out the a squared from the whole shebang, it just becomes an a, and then you're left with a square root of sine squared plus cosine squared, which is going to go to 1. All right, so my t of t is r prime of t divided by its magnitude. You're just looking at negative sine t cosine t. And finding the derivative of that is not hard. Negative cosine t, comma, negative sine t. The added little component or twist is that I now have to find the magnitude of this. Fortunately, though, that's also pretty easy, because that's our Pythagorean identity. Turns out we just get a 1. All right, so the kappa is the magnitude of the derivative of the unit tangent vector, which is 1, over the magnitude of the derivative of the vector valued function, which is a. And so we get the curvature of a circle with radius of a is equal to 1 over a. All right, so whatever the radius is, flip it over and that's your curvature. All right. So not terrible. And you could also kind of rely on that information now. You know, so depends on the way the question's phrased. If I say find the curvature, you could look at it as, oh, circle. Okay, well, I know that the curvature is equal to 1 over the radius, and just write a little statement saying that. Right? You don't actually have to do the work if it's something that you recognize. All right? Like, for example, number 14. I mean, there's a process that you could follow, but kappa is going to be equal to 0 because a straight line doesn't have any curvature to it. All right, so there's no work to do there. I mean, you could do the work to prove it, but it's not necessary. All right. But then you have the circular helix, which, you know, it involves a little bit more, but nothing too crazy, because my r prime of t is going to have a lot of the same base elements as it did in number 12. So negative sine t, comma, cosine t, comma, 0. All right, so r prime of t's magnitude is going to be the sum of these squared values. Now, I'm not going to kill myself doing this because really, I'll fix that equal sign in a second. It's got the same ingredients as my unit tangent vector and its derivative from the last problem. So square this, square that, add it all together, you're going to get sine squared plus cosine squared equals 1. So my magnitude is equal to 1. So there's really no work to do there. All right, and so that means that my tangent vector, my unit tangent vector, is the same as r prime. All right. t prime of t is the derivative of that, which is negative cosine t, negative sine t, and 0. And its magnitude, same ingredients. Again, you start relying on this information so that you can skip a whole bunch of steps. All right? And so I get my kappa value here. Kappa is the ratio of the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector value function, which would be 1 over 1, which is 1. All right? So if you know anything about like standard deviation and correlation coefficients from stat, then you can kind of start to think of kappa as something along the same lines. It really is more of a comparative value than anything else. Right? The reciprocal of the radius, yeah, okay, cool. But, and by the way, this is a unit circle with height. So its radius is really a 1, reciprocal of 1 is 1, right? But we don't really look at that 1 and say, oh, that's curvy or that's not curvy. What we do is we compare it to other values and say it's more curvy than this or less curvy than that. So based on what I got here, you know, going back to the previous page and looking at this, we're looking at this being more curvy than that, potentially more curvy than that, but depends on A. If A is a fractional value, then this will be more curvy. If A is a whole number value, then this will be less curvy. And then on the previous page where we got a curvature of 2, at that location of t equals 0, for I believe this same exact function, or maybe not, this is the one I said to skip. Yeah, for whatever that problem was, at that location, you're looking at something that's more curvy than either of these, right? 13 or 14. Right? So you can determine the relationship between the curvature of different functions. All right, so like I said on the last page, if we're going to skip that one at a point, we'll skip it in general terms too. All right. But that's really the concept of curvature. You know, process-wise, it is what it is, you know, like there's a lot of moving parts, but they're the same moving parts. You follow the steps. You saw I was finding the derivative of the vector value function, then its magnitude, then finding t of t, then finding its derivative and its magnitude, and then creating a fraction. Right? So it's really just a case of, well, I know what I got to do, I just got to do it. Right? Now, motion in space is the last topic. It's a quick one, so we're not really going to belabor this too much longer. Really, I mean, you could read through all of this stuff here. You're definitely welcome to, but I'm just going to jump right to the last little chunk of stuff here, because all of that stuff that precedes this is it's all basically saying that the derivative of position is velocity, the derivative of velocity is acceleration, right? First and second derivatives of a function. So it's just all like how it ties together with vector value functions, which is basically saying you take the derivative of the vector value function a piece at a time, that gives you a velocity vector. Then take the derivative of that a piece at a time, and it gives you an acceleration vector. If you find the magnitudes of those vectors, then that gives you the actual velocity and the actual acceleration. All right. The extra facts is that what we're going to do. When they give us the curriculum for these courses, pretty much every course, they say, and we'd like you to teach some applications of some of the content. And here are some options of things that you can choose. All right. And so I selected Newton's second law because I found it to be interesting at the time, and I think I kind of still do. But I tend to get bored over time, so maybe it'll change at some point. But that's really the only case that we're going to focus on, because I have a couple of examples, a few different types of examples on the next page, but that's the one that we're going to focus on, specifically related to circular motion. Right? So the vector form of a circle, we just talked about it, but we do have room to vary your coefficients surrounding the t value. Right? So A represents the radius, but B, C, and D represent the other attributes of the trig function, which work their way into the actual graph that you create. Right? Specifically related to period, frequency, and any kind of phase or vertical shifting, all right? So we're gonna have to keep that in mind because, well, you'll see. So in number one, it's to find the force acting on a 2 kilogram ball moving in a circular path of radius 3 meters with a period of rotation being 3.7 seconds. All right, so we know the radius is 3. So that's our A value. The 2 kilograms, that's going to be the mass. Force, F equals ma. All right, so if I come up with the acceleration, the magnitude of the acceleration, I just have to multiply it by 2 kilograms and I'll have the amount of force applied, right? So I have to come up with a vector value function that's going to get this job done. Now, this is where sometimes folks having background in physics can work against them, because I've had people just kind of tune out everything that I say related to this and say, oh, just use the physics approach. And I say, okay, cool, I won't be giving you any credit on the test though, because if you solve this problem using a technique other than calculus in some capacity, there really is not any room for me to give you any kind of credit, right? So what I'm gonna do is I'm just gonna, I'll set up my general model, R of t, turn on a pen, R of t is gonna be equal to 3 cosine, well, really 3 cosine of something, comma 3 sine of something. It's just the something is going to change because we have a period of rotation of 3.7 seconds. Now, the period is equal to 2 pi over b. All right, so they're telling us that the period is 3.7. That's going to make the b value 2 pi over 3.7. All right, so since the general model is a cosine bt plus c plus d, all right, this is telling us that my coefficient of t is going to be 2 pi over 3.7. All right, so 2 pi over 3.7, and then I'd have my t. So 2 pi over 3.7 t. All right, so now I have to differentiate. I'm going to take the derivative of this, r prime of t. So a little bit of chain rule. So -3 times the sine of the stuff on the inside times the derivative of the inside. That's going to give me -6 pi over 3.7 cosine 2 pi over 3.7 t. And derivative of sine is cosine, so 3 cosine of all that stuff on the inside multiplied by the derivative of all that stuff on the inside. So we're looking at 6 pi over 3.7 cosine of 2 pi over 3.7 times time. I wrote cosine for the first one, I meant sine. Hopefully I said sine, but I can't even count on myself for that anymore. So that's my velocity vector. I can figure out what the velocity is by finding the magnitude of this vector, maybe chucking in some values. If it's constant, then it'll come out in a wash, but maybe it's variable and I need to know a particular time t. But what I'm after is acceleration, so r double prime of t. So sine goes to cosine. I'm going to end up multiplying by that inner function's derivative again. So we're looking at negative 12 pi squared over 3.7 squared cosine 2 pi over 3.7t. And then all the same crap again, just with a sign. All right, so negative 12, or negative sign, sorry. Negative 12 pi squared over 3.7 squared sine 2 pi over 3.7 t. All right, so that's pretty gross. All right, so this is velocity. I should do that in blue. This is my velocity vector, and this is my acceleration vector. So what I need is the magnitude of that. Now it looks like it'd be pretty much a beast, but it's actually going to clean up very, very nicely. Yeah, we're just squaring a lot of stuff. It's going to look uglier before it looks better, but we're squaring everything. So 12 becomes 144, pi squared becomes pi to the fourth, 3.7 squared becomes 3.7 to the fourth, cosine becomes cosine squared of 2 pi over 3.7t, plus all the same stuff again, just with a sign. All right. So just like we did before, I mean, this is just a beastly looking thing, but just like we did before, we have a common factor that can be pulled out of the whole thing. So go ahead and do that. Pull it right out of the radical. It becomes 12 pi squared over 3.7 squared. When you pull it out, you're left with a cosine squared something plus sine squared same something. Cosine squared plus sine squared is equal to 1, so that ends up being irrelevant, right? Since this is my acceleration, or the magnitude of the second derivative is acceleration, that means I just figured out the a, all right? So the a part of F equals ma. Now it's just a matter of multiplying it by the m, and I have my force, all right? So force is equal to ma, which is 2 multiplied by 12 pi squared over 3.7 squared. So 24 pi squared over 3.7 squared. Now, if you know the units are newtons, then boom, go for it. But if not, and you need the units, so if not, you could just kind of invent the units on the fly, right? Because we start off with meters, right? The unit of time is seconds, so my first derivative, meters per second. My second derivative, meters per second squared. And so when we multiply it by kilograms, we get kilograms multiplied by meters per second squared, which you may or may not know is the definition of a Newton. All right, so I didn't know that. I didn't know that when I was a calculus student. I didn't know it when I was a physics student. I actually didn't know it until I started teaching calculus. All right, and I was like, oh, I keep getting these units, kilograms times meters per second squared, but it's force, so it should be in newtons. So then I just did one of these like, you gotta be kidding me. Let me look it up. Yeah, of course it is. That is what a newton is. All right. So I knew it all along, I just didn't know it, so just for brevity, people write newtons because Newton was like, I'm not writing kgm over s squared every single time, so I came up with all this crap, so it's getting my name. and I respect that. All right. So number 2 has us generalizing this, an expression for centripetal acceleration, A equals v squared over r, of any object following a circular path of radius r at constant speed v. Relate the expression to the angular speed. I'm just going to say w. I forget which one that is. Is it equal omega? Yeah. Looks just like an omega. That's the thing. Like, I always felt annoyed with the Greek alphabet. I'm like, the capitals and the lowercase look nothing like each other. This is so stupid. And then I looked at the alphabet that we use, and with a few exceptions, that's pretty much the same deal. Like a capital D and a lowercase d, nah. H, E, G, A. Like, I mean, there are some exceptions, you know. Q is a nightmare. Yeah. But yeah, it's kind of all over the place also. So it kind of made me feel better. Like everybody's inconsistent too. So this is really just talking about the same idea as that, just in general terms, right? So if I'm talking about angular speed, theta, omega is equal to theta over t. If my general form is going to involve some coefficient of t, what this is telling me is that theta is equal to omega t. Now, I am ultimately looking for acceleration, but they're telling me that that's equivalent to velocity squared divided by r. So I'll worry about that in a minute, because what I need to do is come up with my vector valued function that's going to get the job done. They're saying the radius is equal to r, so that's easy enough. I'm going to come up with r of t is equal to r cosine omega t, comma r sine omega t. So this is actually, I mean, we're working in general terms, but this is actually going to be a little bit easier than the previous case, because it's just like the derivative of omega t. Well, it's not going to be anywhere near as complicated as something like 2 pi over 3.7. It's just going to be omega, right? So r prime of t, which is my velocity vector, is going to be negative r omega sine. That's what I did before. I just copied. I was like, I'll just write what it says there. Omega t. And then r omega cosine omega t. All right, since I'm looking to find the expression for the centripetal acceleration, so this expression, I know that I'm going to need my velocity's magnitude in a sec, so we might as well just get that now. Velocity is going to be equal to the magnitude of r prime of t. Oh, actually, we're looking for velocity squared, so we could even just take this expression and just drop the radical. I'll leave that up to you, like if you want to show that step. So r squared omega squared sine squared omega t cripes, come on, there it is, plus r squared omega squared cosine squared omega t. So I can factor out the r squared omega squared right out of the radical, and that would be my v, because sine squared plus cosine squared is going to 1. But like I said, ultimately, I need v squared, so that's going to be r squared omega squared. So for my acceleration, r double prime of t I'm looking at negative r omega squared cosine omega t comma negative r omega squared sine omega t. And so acceleration is going to be the magnitude of that. Now you can kind of cut the fluff out a little bit here, because really, I mean, after all of this, you know, we did the last example, pretty lengthy. Here, we get past this, and at some point it has to click. Wait a minute, it's just the coefficient. You know, so whatever the coefficient is of your vector, that's the magnitude of it. And really, if you think about it, you're talking about a circular path. The magnitude is the radius. Since the radius is not changing, the magnitude of each of those vectors will be the same and be whatever the radius is. So this is going to clean up. You just drop the negatives. It's going to clean up. You can do all the work, but it's just going to be r omega squared. All right. So if I'm looking for A, we're looking to justify A equals V squared over R. I have what I need. We're looking at R omega squared is equal to R squared omega squared over R. So we actually prove this relationship using vector notation. All right, so, but it's basically the same idea as up there, it's just we're doing a little bit more work. And we also didn't find the force, we just found the acceleration. All right, so, so yeah, that's really it.